the symposium. And now for this opening talk, I will very briefly visit the past of the department, and then I will consider the present state of our department, and then have a look at the future. So what is our roadmap towards the future? So to start, our department was founded in 1967 at Aurorankatu, and the first professor was the late Martti Tienari, who was also the first head of department. And the first years of the department focused on teaching, especially teaching computer science as a minor subject. And then as the popularity of computer science grew, the department expanded towards also major studies as well. So the computer science became a major topic, major subject. And then the research component also grew during the late 70s, and the first PhD degree of the department was granted in 1974. And 1 year after that, we had the first research project running at the department. And from there on, research has been an integral part of our department. And we see research and education going together and forming this connected whole. Then, as time went by, we have of course had numerous highlights and results. And one notable result is the Linux kernel that comes from our department and from the environment of our department. So Linus Torvalds used to study and work at the department, and he started to work on the Linux kernel in '91 and then did the first release in '94. And the department supported this activity, and the first public announcement of the Linux kernel happened at our department. Then to mention some other highlights, so one very interesting and well-known highlight is the Helsinki Institute for Information Technology, so HIIT, that was formed by University of Helsinki and Helsinki University of Technology, so nowadays Aalto University. And HIIT has been combining the forces of the two universities and also branching out beyond computer science into other topics as well, having this kind of multidisciplinary approach in the operation. So HIIT is definitely one of the highlights in our history. And then if we consider the places where our department has been located, so we have been at 5 different places, and after 4 relocations after Aurorankatu, we have then ended up at the Kumpula Science Campus. And that's where we have the largest concentration of natural sciences in the Nordic countries. So our department is very happy at the Kumpula campus, and we are now part of the family there. So to mention some of the evolution of the topics that have been covered at the department, so in the 70s, the research was theory-oriented, so we focused on the theory of programming, systems programming, numerical algorithms, to give some examples. And then in the 80s and 90s, the department diversified towards more applied areas of computer science. And these include, for example, data communications and distributed systems, information management, and then algorithms and data structures. And the diversification has continued since then. So in the early 2000s, we have been looking at mobile computing, data analysis, and bioinformatics. And data analysis and bioinfo, they have formed the basis for data science that we are now doing. So if you consider what has happened in 2010, we have now started to focus on data science, interactive systems, and then security. And these topics, they follow, of course, what is happening in the international setting, and they also follow what is happening in society. So we have a very kind of close interaction with the government and industry, and also the scientific communities. And these then shape the directions to which we are going. And the title for this Jubilee seminar is Bringing the Future into the Present since 1967. And that's what we want to do. We want to be able to develop solutions that are future-proof, that pave way for new solutions, new services. And that's what we have been doing for the past 50 years. And here you see some examples of what we have been able to accomplish here. And this is just a selection. So there are many, many things I would like to report now. But just to give some examples, so we have, for example, the metacompilers of the late 70s. We have Ukkonen's algorithm from 1995. We have the data mining results. And then we have the applications of these algorithms and solutions. For example, applying sequence matching algorithms and string matching algorithms into bioinformatics. So we want to achieve this kind of a spiral, upward spiral, that we build on the known good results and find even better results and new openings in science. That's what we want to do, and that's what we have been doing over the years. To consider some other areas, so for example, in mobile computing, we have worked with all the generations of the cellular technologies, starting from 2G. So at the top left hand side of this slide, you see early GSM data, research equipment, and we are still working on cellular network technologies. Now we are working on 5G. And on top right-hand side, you see a 5G base station, or 4G to 5G base station. And that's what we are at the moment researching. So many highlights, and these go also beyond research. They also include education. And one example of a recent highlight is the MOOC activity, so massive open online courses that we are doing, and trying to understand that what kind of an AI could help our students and teachers in the future. So now I wanted to tell you about the department today, what is happening at the department. And we are at the moment an active society of about 200 people, 200 staff members, including 16 professors. And we are focusing on algorithms and machine learning, networks and services, software, and then data science, building on bioinformatics. These are the active areas of research that also reflect into our education. And we have received good news over the last year. So our department has been highly ranked by many international ranking agencies. And I'm happy to report that at the moment we are #1 in the Nordic countries according to the Times Higher Education ranking, and we are #1 in Finland according to the QS ranking. So we have some good news there. And we have been also working on the outreach towards the society, towards companies. And one highlight here is the Nokia Center for Advanced Research, which started last year, and also based on a substantial donation from Nokia, we have been able to establish a new professor position, Nokia Chair in Data Science. And there I'm happy to report that we have recruited Professor Pan Hui from Hong Kong University of Science and Technology, who will start tomorrow in this new position. So that's a very recent thing. There are also many other activities and events I want to mention. Perhaps I just mention the F-Secure MOOC collaboration, that we did a very popular MOOC with F-Secure on security. And there are many other activities with companies going on and starting. We have also been active at the Kumpula Science Campus. So we have been working on the data science, and we are launching a data science center later this year. And that will be together with Aalto University. We are also working on the MOOCs, and we want to have a portfolio of courses offered to all by our department and our university. So many things are happening. Then what about the future? So what can we say about the next years for the department? And I would want to tell you about our vision. So we have been discussing our vision recently, and currently the vision is the following, that we are architects of the digital future, covering these core areas of our research. And we have certain organizational changes coming up next year. So our name in Finnish will change. So we are now called Tietojen käsittelytieteen laitos, and next year we will be called Tietojen käsittelytieteen osasto. But in English, our name doesn't change. We will still be department next year. And I'm certain that our department will prosper in this new environment in 2018. And I'm happy to report that our department is growing. So at the moment, as mentioned, we have 16 professors. And we have a plan that by 2019, we will have 29 professors. So the department will face significant growth. That's a very positive thing. So we can expand, we can diversify, we can tackle even bigger challenges as a community. And if I have to give these strategic goals for us, for our department for the next years, I would say that they are the following three. They are data science, they are artificial intelligence and machine learning, and then software infrastructure in the wide sense. So these are the key areas in which we are planning significant activities. Within the Helsinki ICT community, within Finland, in the international setting, with the companies. And now I would like to welcome you again to our Jubilee seminar. I hope that you have a really great time here and you enjoy our program. Thank you.
Mr. Vice Rector, distinguished guests, ladies and gentlemen, this was Professor Sasu Tarkoma, our head of department. I'm Patrick Florén, I will be your master of ceremony today. I hope you have all taken this paper. I see so many well-known faces here. I myself have a long history at the department. I actually got employed at the department in 1985, and then I left in 94 and came back 2001. So I see lots of people here who are not anymore at the department, but have come for the event. Very nice to see old friends and new faces. So we have a series of interesting talks coming up. The first one is by Professor Randy Katz, who is a United Microelectronics Distinguished Professor of Electrical Engineering and Computer Science at the University of California at Berkeley. He has done his PhD in Berkeley in 1980 and worked on mobile computing and wireless communications since 1995. His current research interests we will surely know more about in a moment. They are about software-defined buildings and investigating new ways based on machine learning to manage resources in complex distributed systems environments. It could be nice to mention also that he worked for the Bill Clinton administration, that was 93, 94, setting up White House to be online. And he has a long-standing connection with us here. He has been, for many years, the chairman of the HIIT, Scientific Advisory Board. And this talk is also part of what we call the Helsinki Distinguished Lecture Series on Future Information Technology. We have here together University of Helsinki and Aalto University a series of talks where very high-level scientists from all over the world come and present current things. So, a very warm welcome to Professor Randy Katz.
Well, of course, it's a very great honor to be here today to have a presentation to you. What I'd like to speak about today is buildings, energy, and transportation systems and the coming disruption of the industries that they represent. As computer scientists across our careers, we've witnessed tremendous disruption in a large number of different industries. Obviously, telecommunications is one of them, but think about things like retail and bookstores and news organizations and so on. We've had a tremendous impact, for good and for bad, in the way in which the world of 2017 exists. And my talk in part is to extrapolate forward at some of the challenges that will be faced by major multi-trillion-dollar industries in an amazingly short period of time into the future, and computer science is driving those disruptions. So the outline for my talk is, first of all, I have a personal technical interest in what has emerged as being called smart cities. And I think that buildings, energy, and transportation systems, the integration of those, are at the heart of smart cities. And I'll talk to you about that. This leads to some industrial disruptions that are going to take place in the automobile industry, in the petroleum industry, and I believe in the transportation industry as well. So, as computer scientists, this university is world-renowned for the work in developing the operating system technology that is the heart of most of the machines running in the internet world today, Linux. What do we mean when we think about an operating system, not just for our servers and laptops, but for the real world of, again, buildings, energy, and transportation systems? What does the operational software for that kind of world look like? And that will be a major challenge for our field going forward. And I think an element of that is really a vision of pervasive monitoring, modeling, and acting in the real world, in the real time, and at urban scale. And so where does things like machine intelligence fit into the ability to collect vast quantities of information, understand through some kind of processing what that is telling you about the world in order to manage, to control that physical world, to close the control loop? And this is a major challenge for our field today and moving forward. So difficult to see slide, I understand that, but it's an attempt to be a concept picture for what a smart city is about. And elements of the smart city are intelligent buildings that are aware of how they're used and what people are doing in them, and sort of adjust their behavior to their usages. If no one is in the building, don't air condition the building in the summer or heat it in the winter. Make it more energy efficient, make it more controllable. We are inheriting an infrastructure of light switches and things like that when we all have mobile devices that we can use for controlling the lights, the air handling, and all these different kinds of facilities that exist in buildings today. This is the vision going forward of smart buildings. Resilience of cities. In the United States today, there's a gigantic hurricane-induced flood in the southern part of Texas. People are very concerned about how our urban infrastructure responds to natural disasters, things that are very infrequent events, but have a tremendous societal impact. How can information technology assist in the planning, the direction of resources, the effective response to these kinds of emergencies? If you're watching any of this on television, you know, I mean, we're just seeing with images of the inability of society to rapidly respond to the disaster on that size and scale. We need to be able to do better than that, because in the age of climate change, these kind of events are going to be ever more frequent, and we have to get better at that, a major challenge for information technology. Energy systems, of course, we have an ever-increasing sort of introduction of renewable resources into the energy mix. The state of California for one day in 2017 ran entirely on renewable energy this year, which is a major step forward for us in a state of the United States of a population of 34 million people. For one entire day, we ran 100% on renewable. It shows that it can be done. And of course, there are many places in Europe which are very large percentage of the portfolio these days is based on renewable energy, and a commitment to move even forward in that in many places around the world. Smart transportation systems. We spend most of our time in buildings and the rest of our time getting between buildings, it seems. And so the integration of those two infrastructures is very important from an ease of use, from a sustainability of society, from an energy efficiency perspective as we sort of move forward into the 21st century. And of course, the whole theme of this is how to have a lighter load on the resource consumption of the planet as we move forward, sustainability. So some of those societal goals, we want cities that are healthier. We want to understand the sources that lead to bad urban health. In many of the poorer parts of the United States, the air quality is horrendous. Diesel fumes or escape gases from industrial plants. I just saw an announcement that in Houston, a couple of the petroleum plants blew up, within the last hour as a result of some of the flooding that's going on. What are the impacts on the people who live in those areas being in close proximity to sources of very poor quality air or other, dangers? We need to understand that in order to appropriately regulate and respond in those cases to improve people's health. As I already mentioned, resilient cities. We're witnessing what's happening in Houston right now and our inability of a society to be very efficient and fast in the way that we respond to those large-scale natural disasters. Connected cities. We want to know more about what people are doing in the cities, what they think about, how we respond if you're in a government planning role or developing any of these urban scale infrastructures. A key enablement is to understand what people are doing and what the sort of behavior of their life in the city is like in order to try and improve that in the sort of services that are developed. And monitoring and understanding is a very important element of that. And then, of course, make the city more productive for its inhabitants, understand where they work, where they live, where they play, how they have recreation for themselves, and feed that into the planning process and the management of cities. Now, unfortunately, this is a photograph of the approaches to the San Francisco Bay Bridge, which is a bridge that when I drive from home in San Francisco to work at Berkeley, I sort of have to deal with this every day. This is not an example of a smart city when you have to be faced with this kind of urban traffic demands. What are the implications for this smart technology getting into the real world? So this is a report, a rather long-winded summary paragraph from a very interesting study that was done by a think tank based at Stanford University called RethinkX. And I want to bring to your attention what I have highlighted on this slide, the major sort of influence moving forward, or the major opportunity is around that bolded part of the slide. On-demand autonomous electric vehicles owned by fleets, not individuals, in a new business model called transportation as a service will revolutionize urban systems as we understand them. So this is a major trend, highly visible in California, but has the potential to rapidly disseminate itself across the world. It's easy to talk about, well, people have been talking about electric vehicles and Uber ride sharing and all these things for a long time. We kind of understand that they no longer seem revolutionary, but I kind of ask you to put yourself back into where, let's say, Helsinki was maybe 15 years ago with just the sort of dawn of the internet and the integration of the internet with mobile machines, and to think about how revolutionary that has become in the way that it has reinvented businesses and everyone has to have a cell phone and the way that we interact with each other. Who would have guessed that AT&T, that Nokia would own Bell Labs? I mean, who would have guessed that something like that could possibly have happened in the time frame of a couple of decades? So if we're looking forward from 2017 to, let's say, 2030, there are big changes that could be happening, and it's important to try and understand that because it's a role for information technology and computer science. So these industrial disruptions, the first one is the energy industry. The introduction of renewable energy, that 34 million people can run off of renewable energy for one day, or the fact that countries like Portugal and several others are approaching 100% renewable in the way in which they are delivering energy to their population, or the commitments of governments like Germany to move in that direction over the next sort of short number of years coming forward. Very bold moves, but it's demonstrated that it's possible to do with the right underlying markets and technologies. Personal electric vehicles. Again, this is going to have a major implication for the trillions of dollar industry around extracting oil, whether it's from the North Sea or from the Arabian Peninsula. But where the wealth in the world is has the potential to move rather dramatically over the next few decades. And then autonomous vehicles and transportation as a service will change the way and the interaction that we have with cars. When I was growing up, having a car represented freedom, a level of wealth attainment that was a certain social status. When I look at the students in my classes, the 18, 19, 20-year-olds, they're more concerned with having a cool bicycle than a fancy car. And so there's already demographic shifts which represent dramatic changes in our expectations of transportation. So again, our vehicles are emerging as effectively nodes on a deeply digital electronic transportation network. Think of that. Instead of phones, we have internet access devices that we carry in our pocket. Our cars, instead of just vehicles for getting us from point to A to point B, become nodes in an electronic network. What are the implications for the underlying software systems that are going to drive that kind of service capability? So the compelling case for electric vehicles, many leading analysts have made the following statements. This is a quote from Bloomberg News. Electric vehicles become cheaper than conventional cars predicted in the timeframe of 2030. Several manufacturers, including some big ones like General Motors and Volvo, have committed to an ever-increasing percentage of their fleets to be electric. And of course, Tesla is 100% electric vehicles today, and Volvo has made a commitment to move in that direction in the near future. Countries have put forward a goal for the country to be no more diesel, no more petroleum vehicles, again, in a kind of time frame that's in the order 10 to 15-year time frame. So you begin to see these movements away from petroleum-based transportation system to alternatives, in part because of the environmental impact, in part because of the security issues of being dependent on the countries that currently provide us with that form of energy, be it Russia or Saudi Arabia or whomever, and moving towards things which have a more sustainable and lower impact on the environment. And again, this is a chart from a recent edition of The Economist magazine. The bottom projection, which is kind of the, sort of light blue or greenish blue, which is the bottom of that chart, is the number of electric vehicles predicted to be in the worldwide vehicle fleet in the time frame of 2040, and it comes from a petroleum company. Compared to the business company or business analysis company, Bloomberg, which shows both an exponential growth in these, ever-increasing growth, and orders of magnitude higher number of penetration of electric vehicles. I mean, we don't know who's right, but there's a big difference in the kind of analyses that we're beginning to see in terms of these predictions, and a very large part of that accelerating trend begins in the 2025-2030 timeframe. If you look at the sort of climactic impact of electric vehicles, you cannot separate that from the technology that's necessary to generate the electricity in the first place. While an electric vehicle may have very low impact on the environment itself in terms of not generating any hydrocarbons into the atmosphere, if it is fueled by electricity that was generated by dirty coal, that's not a good implication for the environment. So this is a chart from the Association of American Scientists that shows the equivalent miles per gallon, sorry to use that sort of English system instead of metric system, but miles per gallon you would have to have in a conventional gasoline vehicle to have the equivalent impact on the environment in terms of greenhouse gases, factoring in how electricity is generated. And you can see from this chart that in California and the Northwest, you would need a conventional petroleum-powered car to achieve 78 or 75, 73 to 78 miles per gallon to have the same impact on the environment as an electric vehicle in those parts of the United States generated with the sources of electricity available in those parts of the United States. In the Northwest, it's majorly hydropower. In the California, it's increasingly solar, wind, and nuclear power, which you can complain about, but it's not a hydrocarbon-based energy source. And even in the worst part of the United States, which is Colorado, you would still need a vehicle that could achieve 34 miles per gallon, which is very difficult for conventionally fueled vehicles to achieve today. So good aspects for the impact on the environment by switching to electric vehicles and its impact on the electrical grid as well. Another factor people often will point out, well, to buy the same kind of car, I've got to spend in the US, let's say $30,000 to buy that EV compared to maybe $20,000 to buy a compact, sort of gasoline-powered car. The thing that's often forgotten is how complicated conventional vehicles actually are. This is a fuel injection system from the original patent from the 1940s. If you look inside an automatic transmission for a typical car, the drivetrain has something like 20,000 different components in it in a conventional car. An electric drivetrain has 200, 1/100th as much. So a much simpler, much easier to maintain vehicle that has implications for the running life of these things. People often talk about, the limitations of battery technology or the range of these vehicles. It's a big challenge in a state like California where people drive long distances. Well, again, from the Economist magazine, recent data indicates that we are rapidly improving the underlying battery technology, improving both its safety as well as its ability to store in a small area a large amount of energy necessary for propelling those vehicles a long distance. So Panasonic, which it also includes the mega battery factory at Tesla, is showing a tremendous improvement over the next few years of gigawatt hours that would be available inside a typical battery pack. So technology advancing and the cost of those batteries going down as more larger scale industrial capacity is being dedicated towards battery development. The trends are all positive for battery technology. And a graduate school colleague of mine, Bill Joy, was recently highlighted in Wired magazine for finding the so-called Jesus battery, which is small size, high capacity, and highly safe. He is an investor these days and is investing in a technology which is not lithium-based, but alkaline battery-based. So this is one of those holy grails that the engineering industry is pursuing in order to achieve more dense energy storage in a safe package. There's such a huge industry waiting to make use of that battery that the technological resources of the world are really trying to solve this problem. And so things are getting better in the right directions and will happen sooner than we could possibly imagine. Again, in some experience from California, a company called Tesloop, which runs Tesla vehicles between San Diego and Los Angeles, that's a distance of about, a little bit more than 100 miles, as a ride-sharing type application, almost like a personal vehicle bus between those two cities, has been running these vehicles for several years now and has some interesting data recorded in their blog on the reliability and maintainability of these vehicles. So it's an intercity ride-sharing service in the southern part of the state of California. It's been running since 2015. They're collecting vast quantities of information about the vehicles in their fleet, something on the order of 20,000 miles per month. That's a lot of driving. I drive way less than 20,000 miles per year, and I think most people are in that general range per year. That's per month. The first vehicle is still in service. It's a 2015 Tesla, and it has 250,000 miles on it, and the capacity of the battery in that vehicle has only declined by 6% over its 2-year running life. So the battery, the ability to run these vehicles to approaching 1 million miles before they need replacement is certainly there. Can anyone in the audience guess what the largest maintenance cost associated with this vehicle that has 250,000 miles on it has been? Anyone? Tires. The old Nokia. The most expensive item was tires. Maybe that's maybe a growing industry again. Okay, so now let's put on top of that autonomous vehicles. And so here we are in 2017. People have talked about this kind of hierarchy of autonomy all the way to fully autonomous. Today we're in kind of, colleague has a Tesla. It drives pretty safely with hands off on the highway. It is getting smarter and smarter by the day, but it's not really at the level of complete autonomous driving over a very complicated environment in an urban landscape today. But these are things that are predicted to be generally available in the 10 to 15 year time frame in even economy cars. So rapidly, the industry is moving in this direction. And of course, many people have said a Tesla is really nothing more than a laptop on wheels. The way in which these capabilities are enhanced is not to go to the dealership and have the dealership tinker around with the car. It's over-the-air software download to add a new capability to the vehicle. I mean, this is actually, we should be amazed as computer scientists that a safety-critical system like this actually has software updates, and they don't take place on a 6-month or yearly basis. They happen almost on a daily basis, but very, very frequently. Now, of course, Europe, this is actually a photograph from the Netherlands. Some studies that were done by Volvo several years ago now were showing the advantages of autonomous truck convoys in order to do the more simple problem of getting trucks between cities as efficiently as possible. There actually is a slide I have somewhere that one of the most popular job categories in the United States is truck driver, and those people may soon be displaced and disrupted by this autonomous vehicle technology. There's a company called Peloton that has developed basically the sensor package and software package to retrofit to conventional trucks that has shown a significant energy savings by the ability to drive the vehicles very close together and benefit from the sort of air dynamics that are the interplay between the vehicles to cut the resistance of air to the following vehicle because of the make way of the leading vehicle, and that has resulted in a 10% fuel efficiency. Whether trucks will ever get to electric vehicle status, in part because of the weight of batteries and so on compared to the payload weight, remains to be seen. So none of the things that I'm saying are necessarily clear that 100% of vehicles will be EVs and that nothing will be fueled by petroleum. But the major shifts will take place in personal vehicles, predicted by many sources. Now, of course, there's a tremendous history of artificial intelligence and intelligent processing based here in Finland. Surprisingly, problems that we've worked on as a field for decades still have many challenges associated with them. The kind of sort of vision recognition systems that have been deployed in some of the autonomous vehicles have the problem, even with small disruptions in the environment, of still being able to recognize something like a stop sign. So this was reported in a hacker blog just a few weeks ago. Put some white and black strips on a stop sign and the software in the Tesla won't recognize it anymore. Many challenges to make these more resilient and robust systems are there as we go forward. Driver and public safety. This will be a major disruption and impact when the vehicle is driven not by irrational humans, but by, cold calculating software algorithms, at least we hope. Maybe it's only in the United States that you would find this advertisement stickered on a newspaper box that, by the way, gives away a free newspaper these days because no one would pay for a newspaper anymore. Be alert, this is a high industry street for pedestrians and bicyclists. And if you get hit, this is the law firm to call. Only in the United States. But this is, very close to my home, actually, so I took a picture of it. So transportation as a service, you're aware of Uber is in Helsinki, the sharing economy, bike sharing. I've seen these kinds of things here on the streets of Helsinki. You're fully aware of the emergent sort of business models around these kinds of things. What this results in is, pervasive vehicle tracking and knowing where vehicles are and knowing a lot about the transportation, the current state of the transportation system. And some of them have, game-like user interfaces like Waze that are, at least for a while, sort of fun to use until they get on your nerves. And so that's the transportation industry. The petroleum industry also is facing a major shift due to these electric vehicles and the integration of the intelligence of the transportation system. About 20 years ago, Daniel Yergin won a Pulitzer Prize for a book on the history of the petroleum industry and how it's affected the politics of the Western, actually the entire world. And these things are changing. Some predictions from one of the analyst firms is self-driving cars, truly level 5 self-driving cars, maybe for luxury cars by 2021, working through some of the economics of this so that using EVs will actually be cheaper than using a gas-powered car, and using the service will be cheaper than you owning the car in these kinds of time frames of approximately within the next 10 years. And the fact that in 2022, worldwide demand for oil will peak. People have always talked about peak oil in the sense that we couldn't find any more of it. Now people are talking about we don't need it anymore. Demand will peak, it won't continue to grow, which is, remarkable. And this is again from this Rethink X analysis. And it's backed up by a chart from The Economist magazine that shows a flattening as the shift goes towards electric vehicles in the time frame that we're very, very close to experiencing that right now. A slowing growth in demand for petroleum and ultimately, flattening demand. The smart grid, I think many people in the audience are aware of the integration of renewable, distributed energy sources close to where they're being used and the efficiency that would be gained by using those kinds of things. And the fact that these electric vehicles also provide a capability of providing stabilization to the grid for renewable sources. So our electric vehicles are being designed to not just be charged up by the grid, but to provide energy storage for the grid to smooth out any disruptions that are due to a fall off in wind production or solar production. Now, a famous Finnish Formula One driver said, it's a long race and anything can happen. And so while I have presented to you some of these industrial disruptions based on a lot of background analysis that have been done by experts in the field, it's always safe predicting the future because, I may not be here in 10 years to be, sort of did what I'm predicting here just happen in 2027 or 2030. So, but I think that these trends are very important to influence our field in the way we think about our field going forward. So now I want to shift to that question of what does an operating system for the real world look like? People have called these things cyber-physical systems or Internet of Things. The important element of that is that element of pervasive monitoring, connecting our ability to sense the environment to a place where we could do some analysis on it. It feeds into big data, but making that big data processing ability happen in real time. There was a project that I was involved with in around 2000 that had this image associated with it, that the personal computer of the year 2000 consisted of a microprocessor, display, keyboard, memory, and disk, and that you could imagine an evolution of those to better desktop computers that maybe have now become servers and laptops, but that there would also be a revolution in terms of taking these components of the computing system and blast them apart into separate entities that could be found in the physical environment. Displays that were everywhere around us, and the ability to project images everywhere around us, and a pervasive understanding of where you were located and what would be presented to you in terms of that location and how you had moved through the space and who you were and all of those kinds of things. And of course it would be backed up by an information utility that would be both local and remote, available over the internet through wide area networking. So in some sense, you can read into this some of the aspects of smart buildings, smart environments, the arising of applications that run in part in the local environment and mostly in the cloud by this, maybe not such great crystal ball view of the evolution of the field going forward from the year 2000. But many of these elements are things that we can kind of take for granted in 2017. So now let's look at the transportation system. One of the things implied by this pervasive modeling is we want to know where everything is at all times and all the history of those things. That's a lot of data collection that we need in order to do some of these smart city applications. The safety and accident avoidance has to have responsiveness measured in seconds, all the way up to figuring out whether we should build a new bridge or highway to carry the cars, which could be, basically decades to decide those things. How do we collect all that information, analyze it, make it actionable in real time, but also feed it into a kind of analysis that would inform decision makers that are looking at 10-year projects? This multi-scale aspect is very important. And of course, it's geographically distributed. It's not at a single point or within a single building. It's across a city or a metropolitan area that could be measured by 100 kilometers by 100 kilometers. So the size and scale of the data collection and its organization geographically becomes very important. And since we're monitoring everything that human society is doing, of course the security and privacy issues become extremely important in this environment and are a topic of much discussion in the industry and in the technological field today. Oops, sorry, went a little too far. So one of the things that we've done, that my group at Berkeley has done as a past project, is to look at thinking of energy as a network. So everywhere where electrons flow, bits follow, so that you have the ability instantaneously, for example, for a building to understand its energy demand in terms of the various facilities inside the building, the air conditioning system, the lighting system, and so on. It has a historical information that it can predict forward in time. It has the ability to control the demand profiles of the facilities inside the building, and it knows instantaneously what the demand is. It also knows where everyone is, and it can use that as part of the forward-going prediction. Connected to it, it's connected to the electrical grid. Imagine sharing the ability to share information about the current state of energy generation, the sources of energy generation, green versus brown, renewable versus non-renewable sources, the ability to match that information so as to delay or to reduce the demand for certain elements of energy consumption inside the building if energy is either expensive or not the right portfolio mix for your target for sustainability. And as that mix changes to become less expensive or to be more green oriented, then you cool the building, you turn on more of the lights, etc. So we developed a technical architecture to do that as a prototype, but it shows the power of the ability to integrate buildings with the grid, not just to exchange a message of there's an energy emergency, reduce your demand, but to pass between the building and the grid a model of what energy availability will be in the near future, so the building can act on that model to adjust its load demand to match the predicted energy generation into the future. That's a quantitative step forward in the way in which information technology can change the relationship between buildings and energy systems. And to make that active inside the building is a complicated stack of software that understands the various facilities, has models about it, implements control algorithms and so on based on both the model of energy availability matched against the model of energy demand with given that model the ability to shape that demand in response to the available energy coming from the grid, as well as using any local sources that are available. So it's a cyber-physical system. It's kind of an operating system allocating resources, making decisions, building models, acting on those models. It's a prototype for the kind of operating system for the real world. And underlying that is this whole idea of monitoring, modeling, and managing in order to build these sort of smart-scale systems. Now, within this environment, a major shift in our thinking has to be that people work as sensors for us. They are driving around in the environment. They know what the traffic is because they're slowed down on the roads. They're also actors. We can give them information to change their behavior, to get them to take a different route or to do something different. And people are inherently irrational. as behavioral economists have recently discovered. So as a sensor, there's an entire area of citizen sensor. We carry devices that can be used to understand the environment that we're running in. Uber, many studies have been done about the pricing system inside Uber that incentivize drivers to stay on the road, to get up in the morning and provide the service because they're trying to make a certain number of rides within the next 24 hours, as well as we as consumers of that service. It's too expensive, I think I'll walk, or I'll wait a little bit and I'll try again later in order to avoid the surge pricing. But this underlying economics is so revolutionary and different from the way that taxi cabs work in terms of managing the resources that it provides, again, a model of resource allocation and management that will be foundational for computing systems as we go forward, where they involve people as decision makers. Human cognitive modeling. So Rod Brooks just published an article last month in IEEE Spectrum magazine where he said the problem with not autonomous vehicles is their ability to drive around. The problem is us, people, and how we build models that can be active inside those autonomous vehicles that understands Randy's body language as he approaches an intersection. Is he going to step into the crosswalk or not? And so to avoid accidents, they're going to be so conservative that it'll be extremely annoying to us as passengers in the autonomous vehicle because they're going to go through the city so slow and be so careful. So a major challenge is that sort of cognitive processing that we have that sort of understands people's intents and actions and can read it from their body language and all of that is an area demanding a lot more research as we go forward to make these kinds of systems effective. So in the last couple of minutes of my talk here, let me just talk briefly about some of the projects underway at Berkeley that are responsive to this idea of monitoring, modeling, and acting, which underlies the sort of operating system for the real world. It's a project called RISE, and we are attempting a collaborative project involving numerous faculty members to build a secure real-time decision stack. And what that means is, informed by data that is being monitored from the real world, how do we build models that can both evolve in real time and be active in real time to support automated decisions like traffic management and so on, but also have a kind of interface that can be responsive to planners, human beings making decisions that operate at longer timescales than are necessary for the truly autonomous within seconds kind of response. So we want to understand how to move machine learning systems to very low update latency so we can build models fast, and low decision latency so we can use them to make real-time decisions. Big challenges moving forward. And there's a set of software necessary to do this that I'd be happy to talk about when we have a little bit more time. Now, because we want to make these systems work at urban scale, we need some regionalized processing. It doesn't make sense to collect data over 100 kilometer on a square, all in one place, to collect enough of it to do its job. We have to figure out how to make this a highly distributed system. So if you think about providing a transportation system, let's say for Northern California or the Bay Area, it's big. It's more or less 50 miles on a side, many, many square miles. And of course, you're going to regionalize that and have your own sensing, storing, and computing capabilities. And it'll be interconnected in a variety of ways. And as there's more density of data to be collected, it will be further sub-regionalized into microscopic spaces. Doesn't this kind of look like the cellular network a little bit? So we know how to handle load in that world. How do we think about this in the processing world? And there'll be edge devices, of course, and cloud, but in between, something that can deal with this more regionalized or local processing. Some people have called them micro data centers, for example. Now, when you talk about the real world, we also need to integrate with our learning systems the ability to simulate the real world, because that's an alternative paradigm for predicting forward in time. And so simulation has a powerful ability to allow us to train models before we start using them, and to replace computationally intensive elements of those models with lookup as we build the necessary data models. So the integration of the first principles models that are used in simulation with this data-oriented, big data models, which are essentially, sort of a way of classifying data as it comes in to make it fast to look up and decide, will be a major challenge going forward. And just as coming up to my last couple of slides here, just as a sort of summary of some of the pieces that are going to exist in this operating system for the real world, an adaptation layer, which will make all of those heterogeneous sensors and controllers have a common interface in how they present information and can be actuated. They'll be stored. There needs to be metadata associated with that. There are plenty of data-oriented database problems to be solved in collecting and organizing that data. Whether it's a single database, I don't think that'll be the case, but multiple databases that have to be brokered seems like a more likely kind of architecture. We'll need to know where items are, even as they move, whether they're people or vehicles or sensors that pop up in the environment, where are they located. So localization as a first principles service, figuring out where you are and what's next to you so you can connect to it. And the glue that will tie all this processing together will be event-based. And on top of that will be a set of sort of application platforms which will control things and schedule things and provide the necessary presentation layers for analysis, for the interface to simulation, which doesn't just consume data, but also will generate new data to the data stores to drive some of the modeling that will exist in this environment. So let me go on to my summary and conclusions. Yes, it's about big data. It's about collecting all that pervasive instrumentation of human activity to understand society at scale and feed it into our models and to make those models actionable by controlling the environment. So for me, the smart cities, the thing that ties the buildings and energy and transportation together is let's understand what people are doing and let's develop models of how we can control the services to be delivered to those people based on our understanding of it by controlling things, by performing an action. So big data research, make it work in real time and at the scale of potentially millions of independent people operating over many, many hundreds, if not thousands of square kilometers. And integrate simulation with machine learning as a way of predicting forward in faster than real time. People are inherently part of this system. So building cognitive models of how people behave and have our systems understand those models or embed those models in our system behavior is an essential research need going forward. So people are sensors and actors. We know they can be influenced by things like behavioral economics and incentives. You can't control a person. You can't make them do something. You can lead them in the direction which is beneficial for the system we're building. How exactly do we do that? Through information presentation, through economic incentives? How do we do that? This is a fascinating area. So, and again, the autonomous vehicles understanding human intent by their body language and their facial expression and the motion that they're making as part of the systems that we build. And of course, there's a huge policy and social welfare dimension to all of this that we need as technologists to understand as well. From a traditional computer science research perspective, is the system that we're talking about a distributed system, a hierarchical system, a centralized system? It's going to operate across a broad range there. What's the right underlying architecture? When we talk about the Internet of Things, it's not just machines, it's also people. And people as a thing is a lot more difficult to control than a machine as a thing. And we need to understand that. And of course, the entire issue of security, privacy in the context of analytics. So my last slide, the last time I was in this room was approximately 10 years ago, receiving an honorary doctorate from the University of Helsinki. I have to tell you that it was one of the highlights of my scientific career to be honored in that way, and I'm very happy to have had an opportunity to give this presentation to you today. Thank you.
So thank you, Randy. We have a microphone here, so if you have questions in the audience, please raise your hand. If nobody has anything to ask, maybe I would... Oh,
Henry
has something to ask, of course. Go ahead.
Hi, Randy. Thank you, first of all, for such an excellent presentation. Interesting. Now, you didn't mention one thing. You mentioned about the pedestrian recognition, and but actually, when I worked with Daimler and GM at Harman on this, the hybrid traffic is actually much more problematic. So my Tesla can predict another Tesla very well, because two robot drivers can predict the robocode prediction. But having the problem of having, on a long time in the future, of a hybrid human driver together with the robot driver is actually quite a complex problem. And my question is actually very sort of self-serving. Do you know anybody doing any research on this? Because we could not find anything realistically looking at the actual problem of this hybrid traffic nature.
The hybrid traffic nature, I do not know particularly of a particular research group that's working on that, but I have had a personal experience. I was telling Petri about this on the way walking over. A colleague of mine has a Tesla, and we were driving down to Silicon Valley, a group of us in his vehicle, and he did the demo of hands-off driving on the freeway, on the highway, and a vehicle was coming from 2 lanes to the right into the lane immediately to our right. And you could sort of, and I was driving in the passenger next to the driver, and I'm looking at that and I'm thinking, nothing unusual. This is just a vehicle moving. There was nothing to signal to me any sort of nefarious intent by that driver. Yet the Tesla noticeably stuttered. It was being safe. What happens if that car drifts into my lane? So it doesn't have a model of the ability to understand exactly the problem that you're talking about. And it was noticeable. It was not necessarily something that would completely distract a driver from doing the right thing, but it was a sort of thing where, hey, this is not working like you would expect it to work. It's worried about that car. Should I be worried about it? It might be distracting. So I think that what you bring up is a very important problem in this transition. And realistically, it's a long journey and no one knows how it will turn out. Will we have 100% autonomous vehicles by 2030? The probability is there will continue to be a mix. There'll be cars and people on bicycles. Things will not be entirely automated. So dealing with that cognitive modeling, is there a way that someone could have developed a model of tracking that vehicle historically, while we were driving down the freeway together to see this is not someone who is losing their lane or drifting between lanes. It's not, we know intuitively what drunken behavior is, a drunk driver, when we see it, or we're concerned about someone texting and we see them veering. So I think it's a very important problem, and I agree. I mean, I don't have at the tip of my tongue someone working on it. There is a group at Berkeley who is working on robot-human interaction. Anka Dragan is the faculty member leading that. A lot of what they're doing is more like healthcare robotics. I'm an elderly person, and the robot comes to sort of pick me up and take me into the bath. 90-year-old person, and I'm kind of like cranky and nasty to it and angry at it, and how is it supposed to, sort of soothe you in the right way? She's working on those kinds of problems, which are, kind of an instance in some sense of this sort of human autonomous system interaction kind of problem. But it's a very good point that you raise.
So we need just only smart vehicles, we need smart people also.
Yes, people are not necessary, just like San Francisco is not a smart city.
So, other questions? There is one in the back.
So I'm not exactly sure how to word the question, but it's about the pervasiveness of the information being gathered at those smart cities and people who are concerned about their privacy. I'm just wondering how to start tackling that problem.
Yes, so of course, anytime that we're running Google Maps or an application like that on our phones, it's keeping track of our location. That information, we're told, will be retained for a short period of time, 30 days or something like that, before it's thrown away. Who knows how the companies are actually using that. I think we do need to understand how to move towards a model where the user can control how the data being collected by that individual is actually used, how they can be incentivized, maybe economically, to make that data available, what might exist in terms of third-party brokerage. Right now, we have a winner-take-all model. It's Google Maps or Microsoft Live Maps or that kind of thing. And so we don't have competition in that space to really have effective markets for sort of who I am willing to share my information with and at what price that it might make it attractive to me. So there actually is a role for government to play in establishing that if it is perceived as being an important enough societal goal, which I think it is, but through the political process that users should be able to control their tracked information, then there needs to be a regulatory environment put forward by government to create rules of the road for that, on how long it can be retained, or that it can't be retained, or that there are third parties that can collect it and broker it on my behalf, where I may receive a benefit from that in some form. So in part, there's a technology of how to provide that information in a more statistical fashion that doesn't directly identify me, but there are some problems with that are well known, or how we engage with the political community in order to put the right rules of the road in place so a sort of more neutral technical architecture can emerge.
Okay, thank you. Thanks again,
Thank you.
Professor Andy Katz. So let's move forward in the program. The next speaker is Professor Aapo Hyvärinen. He got his PhD from what is now called Aalto University, but in those days was the Helsinki University of Technology in '97. And then he came to University of Helsinki in 2003, professor 2008. He has written some books that are very well known: Independent Component Analysis, Natural Image Statistics, and he is now a professor in Gatsby Computational Neuroscience Unit at University College London and also at University of Helsinki. So he has done pioneering work in neuroinformatics, and he will tell us about neural networks. Go ahead.
Thank you very much, and I'm greatly honored to speak in this seminar. I hope my talk will be at least entertaining. So I'm going to talk about neural networks, which might be considered as artificial intelligence or genuine statistics, perhaps both of them. So the abstract would be, I will basically, most of the talk is about some kind of a description of our current understanding of how one might build artificial intelligence, where we clearly see the importance of learning, especially learning from big data. And this is, of course, these days people use the word deep learning a lot. I will discuss what that actually means, or I will basically discuss intelligence in that framework and how it is related to what used to be called neural networks and why we have a boom at the moment. And yes, the second part, kind of the second message perhaps in this talk, is how this is actually closely related to classical statistical theory and also how it might be related to the brain. So we see actually a lot of different disciplines coming together. So what is intelligence? That is, of course, the fundamental question, but I'm afraid nobody has a very good answer. Basically, when you have something, well, certainly intelligence is some kind of information processing. When it is somehow really cool, really sophisticated, then people tend to call it intelligence. Well, some of the most recent, most fashionable examples are in machine vision, perhaps related to like autonomous vehicles. One of the most underestimated examples of artificial intelligence is perhaps search engines like Google that we use every day. Then another example is fashionable again is games like chess and Go and so on. And of course, machine translation is another very, very practical application that has become, has made great advances quite recently. Of course, the kind of a, let's say, the ultimate goal of intelligence is what is seen in the brain as illustrated on the lower right-hand corner. Do I actually have a point? So I will start by a very brief history of artificial intelligence, a little bit of a caricature really. So perhaps we can go back to the 1940s when intelligence was seen as some kind of a logical inference, using operations like if, then, and, or, and so on. Well, there were certainly dissenting voices over the years, but it took perhaps until something like the 1980s until basically some kind of a counter-reaction to that paradigm was found, which was basically saying that this intelligence is not just logic. Logic is far too limited. The world is not binary. We need much more than some logical operations. And at the same time, well, this was related to the idea that intelligence actually requires imitating the brain. Artificial intelligence requires imitating the brain. At the same time, then, these ideas were brought forward together with the idea that intelligence actually requires learning. Right, so this was the birth of neural networks, basically. But then around 2000, there was a little bit of a counter-reaction to that idea, and people were saying that, no, actually, we don't need to imitate the brain. Learning is actually just statistics. What we need to do is proper statistical theory, new statistical theory, and that's how we can attain intelligent behavior, artificial intelligence. Okay, but now, around 2012, there was a kind of a new paradigm shift, where people were basically saying that we need again something like the brain. My interpretation of this paradigm shift is that it was really an emphasis on nonlinearity. Intelligent processing is highly nonlinear. I will explain a bit later what that means, and this led to the idea of deep learning. So essentially what happened in 2012 was publication of a single paper, which many people trace the start of deep learning to this paper, or at least the start of the deep learning boom. So the idea here is that, well, we want to recognize what is in an image, a very basic machine vision task. We basically want to have a textual description of what, just like a word or two words about what is in an image. So here's some examples. So so here we would have, when the system is given this image, it will respond that it's a mite with the highest probability. It gives some secondary answers which are not that good. Here, it gives again a primary answer, which is that it would be a leopard, and then some secondary answers, and so on. So it actually worked quite well, and this was quite astounding to many machine vision researchers. I think machine vision was actually in a kind of a slightly depressed state. People were thinking that we will never be able to reach anything like human performance. But this actually was rather close to human performance, and some more recent developments claim to have already surpassed human performance in this kind of a particular task. So importantly here, this system was a learning system. It used more than 1 million images together with textual labels. Textual labels very similar to what is being shown here. So, okay, I will try to explain basically what this deep learning means, what are the principles behind that. At the same time, it is basically an explanation of what is the current understanding of artificial intelligence, what is needed for artificial intelligence. First of all, intelligence must be based on learning. Well, this is an old idea. The idea being, going back to the 80s, the idea being that, well, it may be very difficult to program intelligent operations. For example, if you have this kind of an image, how can you actually program, make software that sees that this is a cat? Now, how do you actually, I mean, if you think about it, how do you actually program something that recognizes a cat in this kind of an example? Well, you may perhaps think about like programming a fur detector, an eye detector, maybe a pointed ear detector. But I mean, it's actually very difficult to build any of those so that they would properly work. And you know, there may be even some kind of a conflicting information inside that data. But maybe it would be easier to program a learning method and somehow let the computer do most of the job. So you program a learning method and then show it a lot of cats, really a lot of pictures of cats, and also a lot of pictures of something which are not cats. And maybe the system then, based on this, based on a well-designed learning method, will learn to recognize this much better. Actually, this is an old idea. I had to say that like 10 years ago when I was giving lectures at the department, I was giving a lecture on machine learning, and then I tried to motivate why people have to learn as in machine learning. I said exactly that, well, it is difficult to program intelligent operations. It might be easier to program a computer to learn them. But then I kind of somehow lost faith. I didn't actually know whether this is true. So this was like 10 years ago. But then with the current deep learning boom now, I think we have a lot of empirical evidence, like the paper that I just talked about, that this is actually true. It may not be so that intelligence must be based on learning, but at least intelligence can be, that at least learning is able to produce intelligence. Okay, so what is then learning? Well, one viewpoint is that learning is statistics, maybe just statistics. Well, if you think about like some kind of a very basic statistical, elementary statistics, well, one of the examples is linear regression. So we have here two variables, one on the horizontal axis, one on the vertical axis. We have observations given by the red points, and then in this textbook example, you can actually build a regression line that kind of captures the basic regularity. And now this enables something like prediction. If you now observe something, a new value for the variable on the horizontal axis, you can then predict quite well what is the value on the horizontal axis. Right. Now, could we actually use this kind of principles to perform intelligent tasks? So like this idea of distinguishing, recognizing cats, maybe distinguishing between cats and dogs. Could we perhaps simply look at correlations of some features and the class labels, that is like numerical, some label saying that if it's 1, it's a cat, if it's 2, then it's a dog, or something like that. Well, the current consensus seems to be that this might work, but it only works if we know the right features to calculate from the images. I will have a bit more on the next slide. But the problem is that nobody has really been able to figure out a system for calculating the right features, so this doesn't it's not this simple. So what do I mean here by features? Well, the problem is that real life problems are usually highly nonlinear. And recognition of a cat, for example, is a highly nonlinear problem. That's why this kind of a linear regression methods don't really work unless you are somehow able to calculate first some sophisticated nonlinear functions. Now, what I mean by nonlinearity is that if we actually try to recognize cats by a linear model or recognize anything with a linear model basically uses a single prototype or a single template, like this one. So in the high dimensional space of an image, in the pixel space, you would have something that has maybe values 0 outside of this cat silhouette and values 1 inside the cat silhouette. And then you would try to match this kind of a silhouette to any incoming image. If it's a good fit, then you say it's a cat. If it's a bad fit, then you say it's not a cat. But this doesn't work for the simple reason that the categories that we are talking about in real life, the images are actually highly variable. For example, a cat could be in many different locations in the image. It could have many different postures in the image. Like if you think about this example here, now certainly this kind of a template given in black and white, if you try to like match it to the figure on the left, on the right, well, it is not a good match in any kind of a classical sense of a Euclidean metric, like a dot product or something like that. What we really need to do is to model nonlinear dependencies. So instead of having a nice regression line, we are dealing with functions which are more like this thing here on the right-hand corner. So highly nonlinear dependencies, you can't just fit a linear line and it will not work at all. So, well, another point here is that we actually, this importance of nonlinearity actually necessarily leads to the following point. I will show that in a while, that, well, we actually need big data and big computers. Because, well, if you want to approximate this kind of a nonlinear functions, we actually need models which have lots of parameters. We need a model with a many degrees of freedom. But if you want to learn such a large number of parameters, you actually need a lot of data points. Like if you think about approximating this function here, well, if you think about having just like 10 points, 10 observations, you wouldn't possibly be able to like capture the actual form of this curve. You really need a lot of points, like actually shown in this illustration. If you have a lot of points, then you can actually somehow interpolate and regress this line. So you need big data, essentially. Now, if you need to process big data and you have models with many parameters, then clearly you need big computers. But I really want to emphasize here the kind of the absolute necessity for big data. big computers are not necessarily, not perhaps so essential, and they are perhaps easier to get. They are not really a bottleneck. It is really the importance of big data that is crucial for artificial intelligence. So now let's go. Now, if you want to basically solve some of these problems that I just listed, basically nonlinearity, big data, and so on. Well, one way of looking at that, one way of trying to solve these problems that has been around for a long time is to look at the brain and try to imitate the brain. So the brain has a huge number of cells, neural cells or neurons. They can be conceptualized as being kind of tiny processes, each of which processes information. Here's an image using some highly sophisticated imaging technology. The kind of green thing in the middle is basically like one neuron. So, well, if we try to understand an old way of trying to understand, an old model for trying to understand what neurons are actually doing is to think about these neurons as something that takes several input values and then outputs a single output value. So that perhaps as a first approximation, the output value is some kind of a weighted sum of the inputs possibly put through some kind of a nonlinearity. So in this sense, we can think of the brain as a massively parallel and distributed computer where we have billions of small processes. So how does this all help us in actually doing artificial intelligence? Well, I think the real importance is that this kind of that imitating the brain by what is called neural networks really helps us in solving this problem of nonlinearity, approximating nonlinear functions. So if you build a neural network with many layers, which basically, so we have, okay, so here we have kind of an input coming from the left, and then the data is processed in some way in each layer, in each neuron, then it is feed forward to the next layer, and so on and so on. We can actually model highly complex nonlinear functions. The classic is, even if you take a very simple model for single neurons, given here, where basically the output of one neuron is a weighted sum of the inputs coming from the previous layer put through some nonlinearity, well, some sophisticated mathematics will show you that under some theoretical assumptions, this kind of systems can actually learn to model any kind of nonlinear input-output mappings. And this is really what people talk about when they talk about deep learning. A neural network like this, which has a lot of layers, and thus it has a great capacity for approximating nonlinear functions. So, to summarize the idea of deep learning. So deep learning can actually be seen, well, I think, well, the best way of describing it is to see it as a nonlinear form of statistics. So the deep neural networks are basically able to learn to approximate almost any nonlinear function, and this better than any competing method. Certainly, there are many other methods for trying to approximate nonlinear functions, but if you have high dimensions, big data, then nothing is really competitive with neural networks. But the learning really requires necessarily that we have big data, a lot of data points, and, well, using big data more or less implies that we need big computers as well. But yes, so the neural networks really, okay, actually, logically, I should have had this point after this point here. So the neural networks really are a method for approximating a nonlinear function, but then you have to devise a principle, a method for learning that nonlinear function. How do you actually learn a nonlinear function from data? And there, what we use is simply classical theories of statistics. Ideas like regression or classification, which is actually can be seen as a form of regression, but importantly, then we can do everything in highly nonlinear ways because of the expressive power of neural networks. And yes, it is in some sense perhaps a little bit like the brain. This is a slightly controversial point here. Neuroscientists may not like the idea that it's like the brain. Computer scientists are not so picky, and they enthusiastically say that we are actually imitating the brain. Well, I don't know. Okay, now one interesting question here is that why do we have this deep learning boom now? Because actually most of the theory is from the 1980s, people who worked on this in the 90s, like I did my PhD in the 90s, they think that all this is kind of well known. So what's new? Why boom in starting from 2012? Well, because one reason is that, well, we need big computers. And one of the part of the boom is that people understood how to, well, of course, computers grew certainly bigger than 20 years earlier, but also people understood how neural networks, the computations needed can actually be efficiently parallelized on graphics processing units. So graphics processing units are actually, they have been developed for basically doing graphics on PCs, but then recently people started building kind of a specialized kinds of graphics processing units for using the same technology, but which are specialized for this kind of machine learning computations, and they are, well, much more efficient than what we had ever before. But still, I want to emphasize that even more important than having these big computers is to have the big data. Perhaps if you have big data but not that big computers, you will still have the same learning results just by waiting a bit more. But without big data, it just simply doesn't work. Well, because of the reason that if you have highly nonlinear functions, you must have a lot of measurements basically in order to have meaningful approximations. And of course, these days we can have it. We can get millions of images from the internet quite easily, which was not possible 10, 20 years ago. But there's actually a catch here, which is that to make the conventional neural network methods work, it's not enough to get a lot of pictures from the internet. You also need, the pictures also need to have labeled. You have to know basically the category that you are using in your classification. You have to know from of each image, is this a cat, or is it a dog, or a leopard, or whatever. And so this is the real bottleneck at the moment. Well, both the fact that we always need big data and the fact that it has to be labeled. Of course, in most applications, you can't just download even unlabeled data from the internet just like that. Images you can download, but in many other applications, collecting data is very difficult. And then this labeling here is often even more difficult. Like in a simple biomedical application, you might get a lot of, let's say, CT scans from some source. But then, to be able to use conventional deep learning methods, you would also need to have a clear diagnosis of each CT scan. Is this a pathology? Is this healthy? And that basically requires a huge amount of expert work and is expensive. So this is this is the real bottleneck at the moment, having big data and having the labels. Now, actually, the problem of not having labels can be, to some extent, alleviated by using an alternative paradigm called unsupervised machine learning. So here the basic idea, is that finding labels, cats and whether it's a cat and dog or whatever, it can be very difficult or it can be very expensive. Now, unsupervised simply means that we learn something about the data without having any kind of labels. So in the case of pictures, we just download a lot of pictures, we have no idea what is in the pictures, and we just want to analyze them. Now, then of course we cannot have a classification method. What we can have is methods that somehow explain something about the internal structure of the data. Methods that perhaps learn some kind of highly useful features that greatly simplify any classification that we want to do later, and so on. Well, in Finland we have had a lot of highly influential research on this topic, starting with the self-organizing map. Well, actually starting perhaps a little bit earlier by Kohonen, but anyway, the most famous early result being Teuvo Kohonen's self-organizing map. This may be a bit difficult to see, but the idea here is that it kind of arranges words. It learns to arrange words on some kind of a topographic organization respecting their logical or semantic similarities. I myself have worked with Erkki Oja on a topic called independent component analysis. Here the idea being that it finds some simple linear features from image data. So yes, the Finnish school has been very prominent on this since the 1980s. So this kind of research used to be called neural networks. By some people, sometimes it wasn't called neural networks, but it's neural networks in a slightly different way than the deep learning. Here we don't, in either of these two methods, you don't use neural networks with many layers to approximate highly nonlinear functions. Actually, the independent component analysis here is a strictly linear method. The self-organizing map is nonlinear in some way, but not in the deep learning sense. So, the future, presumably then, is to combine these different ideas and have unsupervised deep learning. This is actually something that many people, many experts in deep learning say these days. They say that we know perfectly well how to do supervised learning, so there's, at least from a theoretical research viewpoint, there's nothing to do. All you need is just get the data from somewhere and then it works. But if you want to make it work better, and especially if you have difficulties in getting data and the labels, then what we really need is unsupervised deep learning, and it's widely recognized that the theory of unsupervised deep learning is in its infancy, perhaps one might say that. It's certainly not at all in a satisfactory state yet. But yeah, this is again something that people are working on in Finland. Actually, here's, Harri Valpola from the Curious AI company has a lot of interesting work on deep learning, using it for various kinds of unsupervised tasks, feature extraction and so on for images. Like here's an example of learning to segment images. I myself have been recently working on combining this idea of independent component analysis with deep learning, which then means that we can actually calculate this kind of independent components using completely arbitrary nonlinear transformations. So, to conclude, the basic message is, well, basic understanding at the moment is that intelligence is possible by learning. Perhaps, I don't know if many people would say learning is necessary. That may not be so clear, but at least we know that intelligence some kind of intelligence, artificial intelligence, is possible by learning. We know how to do it by learning, let's put it like that. So what the most modern methods in this vein combine is actually two different things. One is a nonlinear function approximation, a highly efficient nonlinear function approximation system based on neural networks. But the neural networks in themselves only are able to approximate nonlinear functions, so the learning part, learning theory must come from somewhere else, and these days it really comes from statistical theory. So we see a combination of this kind of perhaps like computer science and statistical theory in this sense. So most of this research is really a revival of neural network theory from the 80s. But, well, now we have big data. While the availability of data was always the bottleneck, perhaps together with computation, but now we have big data and big computers, so now it actually works. But at the same time then, unsupervised learning has become a topic of great interest, because then we need no labels, and it's at least a little bit easier to collect the data, in some cases much easier to collect that kind of data. So it reduces that bottleneck, really. Okay, thank you very much.
So thank you, Aapo. We have a course called Deep Learning in our department this autumn, so welcome there if you're interested. Any questions? There is one, Jani.
So neural networks can learn to identify a cat from big data by showing it millions of pictures of cats, so it works very well. But an actual child learns to identify a cat when he sees it once, and we think that the child is using neural networks too. So what's so different of child's neural networks which can learn to identify a cat from one actual cat object, and then he can identify it for the rest of his life?
Yes, that's a very good question. Actually, several people have pointed out that in the current deep learning experiments, we use much more data than what children need. Not only for image recognition, also for language learning. Any translation systems are shown, or any natural language processing systems are always shown much more data than what children actually hear. Yes, I suppose one part of the answer is that children learn some kind of a more general regularities. So if they had never seen an animal and you show them a single cat, they might not have any clue that what it is actually, and might not be able to recognize or categorize it anyway. But the point is, I think that they have seen many animals or many pictures of animals, and then when they see a new species of animal, they will then be able to recognize that much better. Kind of using the knowledge required from the other animal species and other recognition tasks. Of course, there's a lot of other differences, like for example, a child would actually usually see a live cat. Well, hopefully you will see a live cat, and then the live cat, you will actually automatically then see it from many different angles. And the cat will take many different postures. So even seeing a single cat, you will actually get the equivalent of maybe 1,000, 10,000 pictures of the cats.
Okay, time is running. Thanks again, Aapo.
Thank you.
And our next speaker is Professor Jaak Vilo from Tartu University in Estonia. He's very well known to our department. He will tell you a little bit about it. He's Professor of Bioinformatics in Tartu and leads the Institute of Computer Science. He has a group on bioinformatics, algorithms and data mining. He has his PhD from University of Helsinki Department of Computer Science in 1991. Welcome.
Where's the
1999.
I think I'll try to stand here. Thank you very much for inviting me. It feels really like home. I was also celebrating earning my PhD in this hall a couple of years ago. Celebrities. I myself first came to Helsinki as exchange student out of Soviet-occupied Estonia. The first moment of seeing the free world and anxious to learn everything. And in order to enable that, I started working at the department as teaching assistant. So I spent 1 year as an exchange student, and 1 year later, Martti Tienari had sent me an invitation that I could come back, start PhD. And that coincided a couple of months before Estonia got back the independence. This disturbs me. It's not my presentation. And then I spent totally about 9 years. I left from here to molecular biology laboratories, EBI, and since 2002 I have been 15 years back to Estonia. Unfortunately, there were not many pictures of that time. For whatever reasons, we did not have digital cameras, so not many pictures. The school in here was very strong in algorithms, combinatorial pattern matching. Esko Hukkonen has been mentioned already by the suffix tree algorithm, and I recollect a couple of moments later in my life. 1999, I was in, after I had just left Helsinki, I was at the conference, Recomb, sitting with Esko and Gene Myers in the table. And Gene Myers was very excited to describe Esko how the problem of whole genome shotgun assembly had been solved by ideas from Esko, but already within the company, Celera, in the private human genome sequencing project. So it was very excited. Jim Myers got the Bioinformatics Society Senior Scientist Award a couple of years ago. So the algorithms from here enabled sequencing of entire human genome in random shotgun sequencing manner. Another senior scientist of bioinformatics community just awarded a month ago, Pavel Pevsner, changed the view how the whole genome shotgun sequencing would be assembled. He turned that upside down, turned it. When you go to receive the honor like this in the society of 10,000 plus researchers, you do not have much time, as I do not have in here. The two principles, just to show the random sequences, in one case you want to overlap as much as you can and make them as short sequence that matches all the pieces. What Pavel Pevsner said that is, we don't need that long sequences. Let's make them shorter. Underline those. It's very counterintuitive, but the way how he approached is that let's make the shorter sequences and make the graph out of the relationships and then walk through the graph. So that's the principle, right? I don't want to go into the algorithms really, but why I wanted to show this is that in his presentation a month ago, he showed this slide that had changed his research career forever. Having the S-Kukkonen conjecture on the sequence properties and relating the sequence algorithms that Esko had been working into the different setting of Schmidt and Waterman that they had done about the human genome's physical mapping and showing that these are equivalent. So the school in here had excellent background, fundamental science that has revolutionized human genome analysis in a way. I myself left '99. I went to work at the European Bioinformatics Institute, worked on gene expression data analysis. When I was still here, I was using the excellent environment in here. Linus Torvalds had big memory, 512 megabyte machine, memory machine, which he only used to develop kernel. But I needed that for my yeast data analysis. So I used all of that memory. And pretty much what we did was looking at the yeast, the baker's yeast genome, full genome, trying to find whether there are any signals that may be interesting from the point of view of regulating genes and genomes. So that's what we did in Bioinformatics Institute. From the computational point of view, the genome sequencing has been totally disrupted and revolutionized. We are so used to 100 years of Moore law, doubling the compute capacity every 1.5 years, predating the computers, starting from the mechanical devices. In 15 years, you double that 10 times, you get 1,000 times faster computers, but genome sequencing got more powerful by millionfold in that time. So now the $3 billion project that was there can be done with less than 1,000 euros per genome, a couple of hundred perhaps. The sequencing machines have been taken to the International Space Station, USB stick size. Also, of course, there are also larger machines, but this is the revolution in there. And the question is, what do we do with that? Cost has come down. Do we understand what's in the genome? Genome sequencing is not only sequencing your germline, your maternal, paternal DNA. With the same platform, we can claim that this is a very universal platform. You can sequence not only DNA from your, which we are born with, but you can sequence every single cancer. Every single cancer is different because of the big aberrations of the genomes. Well, in the different cells, you can have different situation. You can sequence RNA levels. There are tens of different types of RNA, turns out, not only the protein encoding ones. You can measure where the proteins bind to the DNA. You can look at the epigenetics, what else is in the DNA than just sequence, what is the structure of the DNA. what is your immune status, etc. So the same technological platform can give you tens, if not hundreds, of different readouts that we can measure. So it is as universal platform as computing is. Well, maybe not as, but very, very universal. And of course, in the data, that generates lots of different views of the data, different entities. We can look at the different relationships between these entities, proteins to proteins, proteins to DNA, proteins to diseases, tissues to diseases, etc. So that calls for analysis which is sort of like network science, multi-layer networks of the biological entities, diseases, health, you name it. Add to that the smart cities, the smart sensors, and then try to understand how all of this affects our health, or how all of this could improve our treatment outcomes. We now have the costs of every individual patient, all the diseases, everything is encoded in the health systems. We can look at when people get ill, what are the costs of procedures, etc. We know that after 50-year-old, we become very expensive, etc. And the goal is to lower the burden of disease, improve the health and treatment. So I've been back to Estonia for 15 years, joining the Estonia Biobank, actually not working at the biobank, but joining the company that was funding the biobank, entered into this VC-funded company startup scene, as well as started to work at the university. Biobank has 5% of the population, over 50,000 individuals, out of whom 2,400 have now fully been sequenced. And all of the data has been genotyped, read about 1 million markers along the genome. So how do we relate that to the disease? Initially, there are extensive questionnaires. Just tell me about your life habits, everything in one questionnaire. You spend 1 hour, encode everything. You can have data registries, which are very detailed coding of information. But this is not how we collect data on the everyday life. These are very bad user interfaces. How would doctors work with such user interfaces? So now with the biobank, actually, the data emerges by itself. It's observational data recorded by the health system, and this data can be linked to the biobank participants, for example, in Estonia. So that means that all the many diseases that we have, individuals do not have just one. There is usually they come in numbers. Usually they come in certain sequences we do not fully understand. You can have in parallel many different treatments ongoing. You take many different drugs, cocktails. Lots of data, lots of valuable information is encoded in free text. If doctors' scribblings are bad in handwriting, it's as bad in typing. But we need to get that data out from these typed documents, and that's one of the places where we do need lots of machine learning as well, that has been briefly described in here. We can start looking at relationships, comorbidities, which diseases come together, clustering individuals to different pathways, how the diseases emerge. If you're a smoker and get this pulmonary disease, do you also get cancers, etc.? So all these techniques from, in this case, from business process modeling, business process mining field, we are trying to apply to the health setting. So the overall goal is to somehow understand the genome, given any traits, or vice versa, from the genome predict the traits, to understand the mechanisms of health, life, the biology, and we need data analysis in all of this. In the recent work, for example, we can now look at all these fully genome sequences, and look at the genes that are related to some adverse drug reactions. You take a drug, but some genes may be metabolizing that drug. If something is wrong with that gene, you may have a trouble. So we can start linking the genetic variants, specific genes, and the variants to the drugs in the center, to the different adverse reactions that they have been causing as recorded in these health data registries. So you can see that in a way we can start building the database whom to avoid giving certain drugs, as warnings at least, right? You have this genome, seems that you should not be given that drug. That might be the first decision that doctor may look up. Before the coffee breaks, etc., let me scare you for diabetes case. Simple Mendelian genes, diseases are caused by a single locus on the genome. They are simple because it's a single cause. But many complex diseases, we do not know about them. And diabetes is one of them. So the models are emerging that take thousands of different gene variants, try to identify by machine learning, link which variants are related, linear regression, try to understand which variants are causing the disease or which ones are protecting, so getting negative scores, positive scores, summing everything together, and we get nice Gaussian distributions of individuals. High risk to the right, low risk to the left. We do not know all the risks, but what we can show from the data is that if you segment that to 20% percentiles into 5 groups, the red end, the 20% top high-risk individuals, in here these 5 groups are shown. On the right always is this high-risk group, but they have been further divided by the lifestyle and the current body mass index. So if your body mass index is below 25, you are very fit and lean, then the risks are low for almost everybody. Certainly, when the body mass index starts to grow, the risk for diabetes increases drastically, and is 3-4 times even higher for those with a poor genetic risk. So we can see that indeed these risks are higher, and more individuals in there acquire the diabetes over the observation period. Take all the individuals that had not diabetes and start waiting, does any of them develop diabetes? And the 2 groups separate. Yes, you develop diabetes more frequently when you have high risk. It does not mean that when you have low risk, you should be eating too much. Take the genetic, we can now compare the genomes, the populations. Finns on this principal component analysis map, high-dimensional data fitted to 2 dimensions, are to the top right. Kuusamo isolate on the very top, the green. The blue is Finns in there, and in the box are Estonians. We are practically the same genetically when we compare the European populations. So quite similar, closest to each other. For some strange reasons or funny reasons, often these PCA plots, which have nothing to do with geography, can be actually linked to the geographic maps of Europe or Estonia. North, south, east, west. So different populations have different composition of the same risk genetics. And we looked at really different populations from Americas, Asias, South Asia, East Asia, Europe. So you can see that on the PCA plot, the populations are quite different. How does the same diabetes risk manifest across these different populations? And this is the answer. The same Gaussian distributions are somehow totally different. That does not mean that every African would have automatically higher diabetes risk than Europeans. Clearly not. But we just do not understand all the background, genetic background and relationship to the disease. But that also means that if I have my genome, just applying one linear regression method does not give me full picture of my disease risks when we talk about complex diseases. And then add to that the lifestyle and all the other information. Exposures to chemicals, maybe some chemical exposure now may give you some different risks in 5 years' time. So doctors and ourselves, we want to get access to the big data. That means that we need some user interfaces to get access to the big data. That makes it approachable by the doctors, by individuals, by us. There must be some decision support developed that has all this artificial intelligence, all the intelligence built in to interpret the big data related to your health and genomics. So where do we get that? Of course, we need some sort of big data for research in order to work with the research data and then come up with these strategies how to interact with the big data. And all the questions about security and privacy are related, they're similar. So privacy preserving or privacy enhancing technologies for data analysis are clearly also needed. So research and innovation really requires collecting of the data. Aapo made the point, we need data to become intelligent about the data. We need to link these different data sets from different sources. Medical system is not ready for all the omics platforms and genomics and all these different variants of different omics. But over the period of time, this will emerge. So we need to get ready on this. That means that we need to have secure environments and be capable of handling of this data to build these decision support systems, be them visualization or intelligent system. We need to start thinking how do we incorporate our self-bearing data from these corporate silos into our regular healthcare databases. And of course, one single country cannot achieve that. No single country can achieve that. We need to compare and share data and analysis. And of course, all of this research is funded by many, many different players. We are collaborating on also with Finland across different international infrastructures on bioinformatics, on biobanks. So this is a global effort. Thank you very much on my behalf.
So, thank you, Jaak. Professor Esko Kukkonen was mentioned so many times. I think we all know him, but in case there is somebody who is not familiar with Esko, so maybe you show yourself who you are. So here is our Dean, Esko Kukkonen, who was mentioned here. Questions? Very fast one, we're running out of time, so.
I catched up a lot of time.
Yes. If not, I have some announcements. Thanks again, Jaakko. So really, we have a very short coffee break because it's only half an hour. There will be coffee served in the foyer on that side, so you go out and to the right, and in the room in the corner where you have windows to the Senate Square and Aleksanterin Katu. But before that, you can see in your program that there is something interesting about historical things in the department coming up after the break. So when you come back to the room, you can grab a book, either in Finnish or in English. So there are two versions. And please be here on time because we will then start with the rector's greetings. Thanks.
So, welcome back. Please take your seats.
I hope everybody had time enough to get some coffee and other refreshments. So we continue our program. No scientific talks anymore. We have other stuff on the table. And we also will change language policy. Our scientific program was in English, and now you may use English, suomea, or svenska, as you wish. The first presentation or first intervention today is from our rector's office. So I warmly welcome our Vice Rector Jouko Väänänen, who is, before being appointed Vice Rector, he was the Dean of our faculty. He's a mathematician. His area is logics, so he knows very well what we have been doing in our department. Please, Jouko.
Dear guests and dear colleagues, ladies and gentlemen, it is a great pleasure and honor for me to congratulate on behalf of the University of Helsinki the Department of Computer Science on the occasion of its 50th birthday. The department is one of the most successful departments of this university. It has excellent results in research, in teaching, and in societal impact. And international rankings give it high grades. I can say as the Vice Rector that the university is very proud of this department. With the spreading of computational methods to medicine, biology, and more recently also to humanities, as we have heard in the excellent talks today, more and more disciplines need cutting-edge computer science. At the same time, the overall digitalization of the society progresses in unprecedented ways and in, as it seems, with increasing speed. This puts computer science in a pivotal position both in modern society and in our university. One of the special strengths of our computer science department is indeed its combination of theoretical computer science with applications in medicine, biology, and humanities. The strategy of this university has digitalization as a strategic focus area at the moment. And in fact, I am in charge of that focus area. I will rely very much on the Department of Computer Science in this project. And I am very much persuaded by the idea of UPI Campus, which I have learned about from this department, which, as I understand it, attempts to make the university a smart university in the sense of the smart city that we heard about in the talk of Professor Katz. I actually started my own studies in computer science when the department was just over 1 year or 2 years old. It was a time of great expectations, and of course nobody could imagine what the future of computing would bring about. We started with an IBM 1620 computer, which filled a big room, and I remember having serious doubts when someone suggested that the entire IBM 1620 would fit in the future in a suitcase. Now, 50 years later, of course, Apple iWatch has more than IBM 1620 in its inside. Late 60s was a time when computer science and also mathematics beginning courses were so full that people sat on stairs, floors, everywhere in the hallways, and you could not get a seat unless you were ready to fight for it. I remember Martti Tienari, who was mentioned, the first professor, lecture to a packed lecture hall in Kirkkokatu how printers of the future will not print characters one at a time with one stroke, but the whole page at a time with one stroke using something mystical he called laser. The audience was in awe. And now, 50 years later, we have, for example, 3D printers. What will we have in another 50 years? Perhaps screens that are paper thin and approach paper in their structure and can be folded into pocket just like an 824 page today. But obviously, I don't know, I'm just guessing. There is an aspect of computer science which makes it very close to mathematics, especially so-called discrete mathematics and logic. The famous P equals NP problem, which the Austrian-American logician Kurt Gödel suggested to the Hungarian-American mathematician John von Neumann to amuse him when he was seriously ill, is still, after more than 60 years, open. It is not an engineering problem, but rather what is called a complexity problem, and can be formulated as a problem of the existence or non-existence of certain kinds of algorithms. The word algorithm has become recently so popular that even politicians talk about it, and newspapers. Algorithms have been known, of course, for thousands of years, but the applicability of algorithms in everyday life by means of microprocessors have put this concept in the limelight. As is well known, many things about e.g. bank security depend on the non-existence of certain kinds of algorithms. But we do not know yet whether the non-existence is a fact or just difficult to violate, because we don't know whether P equals NP or not. Maybe the P equals NP problem is like Fermat's last theorem, a very simple problem to formulate but takes hundreds of years to solve, and the solution may make unexpected detours through so far uncharted territories of science, just like the solution of Fermat's problem traverses through many fields of mathematics with no apparent connection to the original problem. Indeed, it is characteristic of computer science that it leads us to notoriously difficult theoretical problems with potentially devastating consequences. Again, something we heard about today and will perhaps hear later. I stop here and just note that the Department of Computer Science was timely and popular when it started at the time when man flew to moon and back. It became strong and important, remaining and getting even more popular during the first 50 years. And it will hopefully become even stronger and get even more popular during the next 50 years. I wish the department most successful future. Thank you.
Kiitoksia, vararehtori Väänänen. Next, we will have some interesting notes by Professor Emeritus Jukka Paakki. Jukka Paakki blev doktor från Helsingfors universitet 1991 och var sen alla möjliga ställen, Linköping och Jyväskylä och Karlsruhe, men var också chef för vår institution, oli laitosjohtajana, sitten oli varadekaanina 2007-09. Ja hän on kirjoittanut useita kirjoja, tämmöisiä historiateoksia, muun muassa tämmöinen hauska teos Rupisia bittejä, karmeita kaavioita, unelmia ja toimistohommia, joka on meidän laitoksen historiikki vuodelta 2011. Sitten hän on kirjoittanut Opista tieteeksi, Suomen tietojenkäsittelytieteiden historia. Uusin kirja ennen tätä on Arto Salomaa, äijän näköinen matemaatikko. Ole hyvä, Jukka Paakki.
Kiitos, thank you. This presentation will be given in Finnish. So unfortunately, those who don't understand Finnish may have it a hard time to follow the talk, but you can follow the theme by reading the current history book just published today called Small Memory Dumps. You can find it outside the door, so please get a copy from there. Jouko tuossa jo lausui kauniita sanoja laitoksesta. Jatketaan samoilla linjoilla. Mä nyt lyhyesti kerron laitoksen historiasta siltä, kun se omasta näkökulmastani ja toivottavasti muidenkin näkökulmasta on näyttänyt 50 vuoden ajalta. Ja jottei mene pelkästään muistivarassa, niin on toimitettu kirja, jonka nimi on Suppeita muistivedoksia 67-17 suomeksi. Laitoksesta on tehty 2 aikaisempaakin historiikkia, 1 tuossa mainittiin, mutta nämä 2 aikaisempaa on sen verran hepposia tekeleitä, että nyt tehtiin parempi. Ja laatu on tällä kertaa varmistettu sillä tavalla, että tähän on kirjoittajiksi rekrytoitu 10 parasta asiantuntijaa, jotka Suomenmaasta löytyy, ja heidän kuvansa on tuossa kalvolla, ja heidän nimensä löytyy sitä historiikkiteoksesta. Kiitoksia kaikille kirjoittajille vaivan näöstä. Minkä takia tämmöinen ihmeellinen tietojen käsittelytieteen laitos ylipäänsä piti perustaa? Onko siinä mitään mieltä? No historia alkaa tietokoneiden historiasta. Nyt on vähän erimielisyyttä siitä, mikä on maailman ensimmäinen tietokone. Mutta yksi hyvä ehdokas on Colossus, joka on tuossa vasemmassa yläkulmassa, valmistui 1943 Isossa Britanniassa sotilaskäyttöön murtamaan saksalaisten salakirjoituskoodeja. No, tietokoneet yleistyi pikkuhiljaa 40- ja 50-luvulla, että rakennettiin lisää ja Suomeenkin ensimmäinen tietokone otettiin käyttöön vuonna 1958 Postisäästöpankissa IBM 650. No, kun tietokoneita tuli, niin niitä piti osata käyttää ja piti tehdä jotain, ja siihen tarvittiin osaavaa henkilökuntaa, ja niinpä koulutusta piti panna pystyyn. Aluksi tätä teki maahantoimittajat ja tietokonefirmat, mutta sitten pikkuhiljaa yliopistoihin haluttiin tätä toimintaa, ja niinpä vuonna 1962 perustettiin maailman ensimmäinen Computer Science-ohjelma Yhdysvaltoihin Purdue'n yliopistoon. Suomi ei ollut hirveän paljon perässä, nimittäin jo vuonna 1965 Tampereella toimineeseen yhteiskunnalliseen korkeakouluun perustettiin tietojen käsittelyopin laitos. Tämä korkeakoulu muutti nimensä seuraavana vuonna Tampereen yliopistoksi. Tuon hankkeen yksi puuhamiestä Seppo Mustonen lienee paikalla, ja häntä voidaan kiittää paitsi tästä loistavasta operaatiosta saada tietojen käsittelyoppi Suomeen yliopistoihin myöskin oppiaineen nimestä, koska tietojen käsittelyoppi lanseerattiin silloin tieteenalan käännökseksi Computer Scienceista. Sitten hän pikkuhiljaa todettiin, että ei tämä mitään oppia ole, kyllä tämä tiedettä on siinä, missä muutkin oikeat tieteet, ja niinpä vuonna 1994 opetusministeriön suosituksesta oppiaineen nimeksi muutettiin suurimmassa osassa yliopistoja tietojen käsittelytiede, niin meilläkin, ja laitoksen nimi muuttui. No niin, Seppo on siis näin täällä, ja toinen tässä kalvolla esiintyvä guru on Reino Reiska Kurkisuonio, Suomen ensimmäinen, itse asiassa Pohjoismaiden ensimmäinen tietojen käsittelyopin professori. Hän hoiti sitä Tampereen virkaa aluksi, ja sitten hänet nimitettiin vuonna 1967 tähän. Hyvä Reiska, häntä voitte läimiä hartioille ja pyytää nimmaria tuossa cocktail-tilaisuudessa, hänkin on paikalla. No, Tampere voitti tämän kisan, mutta kaukana ei tullut Helsinki, hyvänä kakkosena kuitenkin, jos ei nyt tällä kertaa ykkösenä. Helsingissäkin oli tietokoneita. Erityisesti täytyy mainita tämmöinen historiallinen merkkiteos kuin Esko, ensimmäinen Suomessa rakennettu tietokone, jota rakennettiin vuosina 1954–1960 matematiikka-konekomitean toimesta. Se oli hieno hanke. Lopputulos tosin oli sen verran huonolaatuinen, että ei sitä Eskoa lopulta hirveän paljon käytetty. Se luovutettiin Helsingin yliopistolle vuonna 1960 ja siirrettiin sitten pikkuhiljaa varastoon 1963 ja Tekniikan museoon 1970, jossa sitä voi käydä ihastelemassa. Sen sijaan, kun ei Eskosta oikein mihinkään ollut, niin hankittiin oikeita tietokoneita myöskin. Ensimmäisenä vuonna 1961 Vegematic 1000, sitten vuonna 1962 IBM 1620, jonka Joukokin mainitsi, ja sitten vuonna 1965 Vegematicin korvaajaksi Elliot 803B. Ja tietenkin näitäkin tietokoneita piti jonkun osata käyttää ja jotain niillä tehdä, ja senpä takia opetusta pantiin pystyyn pikkuhiljaa Helsingin yliopistossa heti vuodesta 1961 lähtien, jolloin tuo ensimmäinen kunnon tietokone hankittiin. Ja sitten näiden tietokoneiden käyttöä, hallinnointia, opetusta ja vähän tutkimustakin koordinoimaan perustettiin vuonna 1960 laskentakeskus, joka on erittäin tärkeä toimija ollut kaiken tämän ajan. Mutta sitten alkoi ehkä näyttää siltä, että ei laskentakeskus yksin pysty vastaamaan kaikesta massiivisesta tarpeesta, ja kun Tampereellakin oli tämmöinen laitos ja tämmöinen professori, niin semmoinen piti saada Helsinkiinkin, ja niinpä laskentakeskuksen johtokunnan aloitteesta Helsingin yliopistoon perustettiin tietojen käsittelyopinlaitos, joka aloitti toimintansa 1.9.67, eli huomenna on virallinen 50-vuotissyntymäpäivä. Tuossa on laitoksen ensimmäinen opetusohjelma lukuvuodelta 67-68, ja niin kuin nähdään, niin laitos oli silloin peräti 4 luennoijaa, Martti Johannes Tienari, Veli Jaakko Nummi, Eero Ilmari Peltola ja Jorma Olavi Torppa. 1.9. vuonna 1967 oli perjantai, ja jos ei silloin lintsattu, niin kautta aikojen ensimmäinen tietojen käsittelyopin luento Helsingin yliopistossa on ollut Veli Jaakko Nummen perjantaina 1.9. kello 11-12 pitämä peruskurssi IBM 1620 tietokoneen ohjelmoinnista. Ja vaikka se olisi lintsattukin se perjantai, niin sama kaveri piti seuraavalla viikolla samanlaisen luennon, että joka tapauksessa Veli Jaakko Nummi on ensimmäinen tietojen käsittelyopin luennoija Helsingin yliopistossa. Että pientähän se alkuun oli, 4 lähdettiin liikkeelle ja pikkuhiljaa sitten kasvettiin. Laitos on toiminut 5 eri toimipisteessä tähän mennessä. Ensimmäinen oli Auroran kadulla pari kuukautta heti 1967. Se kävi ahtaaksi, sitten muutettiin 10 vuodeksi Töölön kadulle, siitä vajaaksi 10 vuodeksi Tukholman kadulle Aurataloon. Sitten pitkäksi aikaa 17 vuodeksi 1987-2004 Teollisuuskadulle ja vuonna 2004 lopulta muun tiedekunnan yhteyteen Exactum-rakennukseen Kumpulan kampukselle, jossa laitos tälläkin hetkellä toimii. Ja aina näissä muutoissa viimeistä lukuun ottamatta laskentakeskus on ollut messissä, tai mitenpä se meneekään, käsi kädessä on menty ylä- ja alamäet. Ensimmäiset tutkintovaatimukset on tämän näköisiä. 60-luvulla kuulemma ATK-ala oli ohjelmointia ja systeemin suunnittelua. No meidän laitos ei tästä systeemin suunnittelusta nyt hirveästi perustanut. Siellä on kyllä automaattisen tietojenkäsittelyn peruskurssi approbaattorissa heti läsnä, mutta sitten myöhemmissä cum laudessa ja laudaattorissa, joka käynnistyi 2 vuotta myöhemmin, niin eipä sitä hirveän paljon näy. Se annettiin nyt sitten muiden hoidettavaksi. Jyväskylässä ja Tampereella näitä asioita harrastettiin enemmän. Meidän laitos keskittyi computer science ydinalueisiin, jota siihen aikoihin määriteltiin. No tuosta te nyt näette, mitä silloin opetettiin. Ehkä nykypäivän valossa merkille pantavaa on, että cum laudessa ja laudaattorissa oli pakollisia elektroniikan ja matematiikan kursseja, toisin kuin nykyisin. Ja toinen merkille pantava seikka on, että kyllä silloin oltiin aika valveutuneita, että tässä on puhuttu aikaisemmin tuossa tiedeosuudessa tekoälystä tai mitä se nykyään onkaan, mutta kyllä jo vuonna 1969-70 oli mahdollista suorittaa keinotekoisesta älykkyydestä ja kybernetiikasta erikoiskursseja. Ei tässä nyt hirveästi ole eteenpäin menty tästä näkökulmasta. Laitos, niin kuin tuossa sanottiin, niin keskittyi ensimmäisenä vuonna opetukseen. Piti saada henkilökuntaa firmojen tarpeisiin ohjelmoimaan niitä koneita ja vähän suunnittelemaankin. Mutta tietysti pikkuhiljaa kun yliopistossa ollaan, niin piti jotain tutkiakin ja pikkuhiljaa tutkimuskin pääsi käyntiin. No alkuun laitoksen opettajat ja tutkijat, kun eivät olleet tietojen käsittelyoppia koskaan vielä opiskelleet, niin tutkivat sitä, mitä katsovat omikseen, eli lähinnä matematiikan ja fysiikan sukuisia aiheita, koska olivat taustaltaan matemaatikoita ja fyysikoita pääasiassa. Senpä takia laitoksen ensimmäinen väitöskirja, joka mainittiin myöskin jo aikaisemmin vuodelta 1974, Seppo Linnaimaan tekemä, käsitteli liukulukulaskennan tehostamismenetelmiä, eli oli numeerista analyysiä pikemminkin kuin computer sciencea sinänsä. Ansiokas väitöskirja toki, ei siinä mitään, mutta aiheeltaan ei ehkä nykyisin laitoksen repertuaariin kelpaisi. Mutta onnea Sepolle siitä, että silloin oli muut tuulet. Ja hän väitteli 30.8.74, eli melkein tasan 33 vuotta sitten, että hauska sattuma toikin. Tässä kuvassa on varsinaisia supertähtiä, joista ainakin yksi on tänäänkin paikalla. No nyt puhun vähän noista kahdesta poissa olevasta, kahdesta vasemmanpuolimaisesta ukkelista. Vasemmalla on Martti Tienari, joka täällä on tietysti mainittu. Hän oli laitoksen ensimmäinen professori, nimitettiin virkansa 1969. Toimi sitten laitoksen esimiehenä yli 30 vuotta lyhyitä poissaoloja lukuun ottamatta. No, Tienari oli loistava hallintomies ja mitä parhain johtaja. Hän piti laitoksen puolia, hankki resursseja, paljon opetuskuntaa, rahaakin. Toisaalta sen lisäksi hän tiesi kaiken kaikesta, oli oikein paremman sortin besserwisseri, eli luonteeltaan selvä fyysikko. Hän oli kuitenkin taustaltaan matemaatikko hieman yllättäen, väitteli matematiikasta vuonna 1962 ja siirtyi sitten tietojen käsittelyoppiin sen, mitä sitten vääräuskoisena enää vanhemmilla päivillään kykeni. Mutta hän on laitoksen perustaja ja tämmöinen kantaisä, että hänen merkitystään ei voi väheksyä. No toinen vasemmalta on sitten vielä suurempi stara, hän on Donald Knuth, joka on yksi näitä tietojen käsittelytieteen varsinaisia kansainvälisiä merkkihenkilöitä. Ja hän liittyy monellakin tapaa laitoksen historiaan. Esimerkiksi yksi hänen menetelmistään on täällä Seppo Linnaimaan väitöskirjan analyysin kohteena. Eli Knuth teki myös tämmöistä liukulukulaskentaa nuoruudessaan. Sitten hän on kirjoittanut, tai aloitti vuonna 1968 kirjoittamaan kirjasarjaa The Art of Computer Programming, joka kolmiosaisena oli Suomen kaikissa tietojen käsittelyopinlaitoksissa perusoppikirjana hyvin pitkään. Ja poikkeuksellista oli se, että siinä ei nyt pelkästään opetettu ohjelmointia, vaan suurempia rakenteita, näitä algoritmeja ja tietorakenteita, jotka tässäkin on jo mainittu. Erittäin perustavaa laatua oleva saavutus ja merkkipaalu tietojen käsittelyopin historiassa tai tietojen käsittelytieteen. No sitten tämä Knuth määritteli vuonna 1968 ohjelmointikielten käsittelyyn ja automaattiseen kääntämiseen soveltuvat attribuuttikieliopit, ja niiden pohjalta käynnistyi vuonna 1975 laitoksella ensimmäinen itse asiassa Suomen ensimmäinen iso tietojen käsittelyopin computer science-projekti, niin sanottu metakääntäjäprojekti, josta on juttua tuossa historiikissa. Ja se metakääntäjäprojekti oli rautaa, paitsi sikäli, että se oli ensimmäinen ja suurin ja kaunein, niin se tuotti kyllä loistavia tuloksia. Se oli laitoksen tutkimuksen lippulaiva pitkään ja tuotti monta tohtoria. Ensimmäiset tohtorit väitteli 70-luvulla ja viimeinen sitten 91. Ei sen takia, että aihe olisi enää ollut silloin hirveän akuutti, mutta väittelijä oli sen verran hidas ja saamaton, että siinä meni aikaa. Mutta siis erittäin pitkä projekti kaiken kaikkiaan. Eikä siinä vielä kaikki. Tämä Knuth on myöskin kehittänyt ladontajärjestelmän, jonka avulla on suurin osa laitoksen ja vähän muidenkin tieteenalojen tieteellistä julkaisuista tuotettu LaTeX-järjestelmän avulla. Todellinen niin kuin pelimies. Laitos laajeni pikkuhiljaa 70-luvulla Tienarin rautaisen ammattitaudon ansiosta. Tämä porukka ei ole suinkaan Kakolasta eikä rauhan osastoilta, vaan tässä on laitoksen opettajakuntaa vuodelta 1981 linjoittain. Silloin laitosta jaettiin linjoihin, koska se oli aika suuri ja tarvittiin vähän organisaatiota. Tuossa on kopsit, käyttöjärjestelmäporukka, kielot, ohjelmointikieliporukka ja tilhit, eli tiedonhallintahemmot. Lisäksi oli vielä matit, joita on osa täällä paikalla. Jostain kumman syystä mateista ei ole säilynyt arkistokuvaa, mutta täällähän sen voi ottaa, kun matit on paikalla oikein kaikin kaksin kappalein. Laitoksella toimi myös huvitoimikunta, joka organisoi laitoksen yhteisiä menoja. Kaiken näköisiä bileitä, urheilutapahtumia, pikkujouluja ja muuta mukavaa 70- ja 80-luvulla. Muun muassa kaiken näköisiä siis urheilukilpailuja. Tutkinut niitä tuloksia, niin keeloja saatiin nurin, mutta ei, kyllä golfpallo ei koloon mennyt, ei sitten millään. Että siinä olisi ollut vähän parantamisen varaa. Laitos on ollut erittäin innovoiva jo alusta lähtien, kun ei alussa ollut oikein monisteita eikä oppikirjaa, paitsi se Knutin juttu. Ne oppikirjat tehtiin itse, luentomonisteet. Laitoksella on kehitetty paljon omaa tietotekniikkaa opetusjärjestelyihin ja muihin. Muun muassa 80-84 Mikko 3 koneeseen tuommoinen mopo, monikäyttöpääteohjelmisto, erittäin suuri hanke, joka oli paljon muissakin Suomen yliopistossa käytössä. Linux was invented here, se on mainittu. Ja sitten on tehty tietysti tieteen saralla paljon hyviä tutkimustuloksia, niin kuin kaikki tunnistaa. Tuossa on tekstin käsittelyyn soveltuva loppuosa puu, johon on vuonna 1995 kehitetty maailmankuulu ukkosen algoritmi, sekin on täällä mainittu. Lisäksi laitoksen parhaimpia tutkimusaloja on metakääntäjiä. Näiden algoritmien lisäksi on ollut ainakin liikkuva tietoliikenne ja tiedonhallinta yleisesti ottaen ja erityisesti tiedon louhinta. No, laitos oli hyvä jo alusta lähtien, mutta parhaimmaksi se nousi noin 2000-luvun alussa keräämällä kaikki mahdolliset kunnianosoitukset ja palkinnot, mitä Suomessa ylipäänsä on ollut jaossa. Oli 2 akatemiaprofessoria, 2 tutkimuksen huippuyksikköä, 2 kertaa peräkkäin yliopistollisen laatuyksikön, yliopistollisen koulutuksen laatuyksikön status, niin kai se meni virallisesti, ja muita palkintoja, suunnilleen kaikki, mitä nyt saatavissa oli. Eli laitos on 2000-luvulla ollut eittämättä Suomen paras laitos, niin kuin Joukokin tuossa suunnilleen sanoi, tai ainakin tarkoitti sitä. Ja varmaankin myös maailman paras, suoraan sanottuna. No sitten laitoksen kyljessä toimii vähän muutakin, on tämä HEAT, joka mainittiin. Meidän ja Aallon yhteinen tutkimuslaitos, Helsinki Institute for Information Technology, 1999 perustettu, tekee loistavaa tutkimusta. Ja sitten voisi mainita tämmöisen linkkiresurssikeskuksen, joka on 2011 perustettu lasten ja nuorten tietojen käsittelytieteelliseen opetukseen keskittyvä porukka, joka myös kehittää laitoksen loistavia MOOC-kursseja, jotka on kansainvälisesti parasta A-ryhmää tietenkin. No, kaikki hyvä loppuu tai keskeytyy aikanaan. Laitos on käynyt monta erilaista vaihetta ja seuraava vaihe päättyy 2 kuukauden päästä, koska Helsingin yliopiston hallitus sen sijaan, että olisi päättänyt antaa kaikki rahat Suomen parhaalle laitokselle, niin päätti lakkauttaa sen muiden mukana. Niinpä ensi vuodesta lähtien ei ole enää olemassa tietojen käsittelytieteen laitosnimistä yhteisöä tai instituutiota, vaan osasto tai vastaava, koska rakenne muuttuu. Mutta ei se mitään, tietojen käsittelytiede ei kuole laitoksen mukana, vaikka niin voisi ehkä luulla. Päinvastoin se varmaankin nousee entistä suurempaan kukoistukseen, niin kuin tuossa tiedeosuudessa kuultiin, näitä tulevaisuuden visioita. Miten tulee käymään, on tietysti hyvä arvailla. Tähän loppuun voidaan palata vuoteen 1969 ja laitoksen ensimmäisen professorin ja esimiehen virkaan astujaisesitelmään, jossa hän visionäärisesti maalailee tietojen käsittelyopilla ruusuista tulevaisuutta. Analogiana höyrykone veikkaa, että tietokoneesta tulee höyrykoneen tapainen keksintö. Ehkä jonain päivänä näin tulee käymään, emme vielä tiedä. Ja samoin hän sitten ennustaa, että tietokoneen vaikutus tieteen kehitykseen on jonkinlainen, mikä se tulee olemaan. Siitä voi esittää arvailuja. No, näitä arvailuja tietojen käsittelytieteen osasto tulee jatkamaan ensi vuodesta lähtien ja joskus nämä arvailut sitten konkretisoituu absoluuttiseksi totuudeksi. Kiitoksia.
Kiitos mainiosta esitelmästä. Jos ette ottaneet kirjaa, niin ottakaa kun poistutte täältä. Seuraavaksi on ihan muuta asiaa tiedossa. Sitä tulee meille selostamaan, että mitä se on. Meidän professorimme Hannu Toivonen. Hannu Toivonen is a pioneer in data mining and is conducting research in data science and computational creativity, and he's leading our new master program in data science. Hannu, you can tell what's going on.